Hello, students. Welcome to the physics classroom. Today, we are going to learn work and power. Work and power. We are going to start with work. Work in physics is defined as force times distance. Force times distance. That's work. I can give an example to make sure that we understand this concept of work. Okay, so I'm going to use the following example. We have a surface and we have a crate. So there is a crate here of mass 2 kilograms. There are forces acting on the crate. There is a 5 Newton force, 5 Newton force, and there is a 2 Newton force acting in the opposite direction. There is gravitational pull pulling downward. This is Fg. And let's call this one pulling force. And this one will be force of friction equal to that. Let me see. Yeah, okay, force of friction equal to 2 newtons. And the pulling force is 5 newtons. There is also a support force. Usually support force is due to the surface on the crate. The support force is here. The box will accelerate to a certain point. For example, here we're just making up a final position. So this will be the final position of the box somewhere there. Now the box will move through some distance. So let me draw a distance from here to there. This will be the distance traveled. Let's assume this distance is 1.5 meters. That's our distance there. The question is, what is the work done by each force? Usually when we talk about work done, we must specify the force. Here we have to ask what is the work done by the pulling force? What is the work done by gravitational pull? What is the work done by the support force? And what is the work done by the frictional force? It is very important to specify the force. Don't just ask what is work, no, but you must say what is the work done by the pulling force, what is the work done by the gravitational force, what is the work done by the support force, and what is the work done by the frictional force. Specify the force. Or you can also ask what is the work done by the net force acting on the 2 kilogram crate. So we are going to answer these questions. Next slide. First of all, let's start with the work done by the pulling force, 5 Newton force. So work done by the 5 Newton force, that's the pulling force. This force is acting to the right, so we are going to put plus 5 newtons, and then times is the distance was 1.5, 1.5 meters. And when you do that, we get 7.5. The units are newtons, and then we have meters here. In physics, a Newton meter is given a unit called joule. A joule is the unit of work. So the work done is given by 7.5 J, joule, like this. All right. Now let's move on to look at the other force is the frictional force. This one here. What is the work done by the frictional force? All right, so let's see. The work done by force of friction will be, the force of friction is acting to the left, so be minus 2 newtons, and then times distance is 1.5 meters. If you do this, you're going to get your answer as minus 3 Newton meters. And remember, a Newton meter is 3 joules. Now let's go back and look at the work done by the gravitational force. Now we look at the gravitational force. Okay. So work done by force of gravity will be what? So that one will be gravitational force is mg. Let's write mg here. And since it's acting downward, you have to put a minus sign here. The force of gravity acts downward. And we have to multiply by the distance. We are going to talk about distance. Okay. Now here, even though we can have numbers, for example, if we have the mass was 2 kilograms and the acceleration due to gravity, let's take 10 meters per second squared. Our distance here, if you look carefully at the problem, we cannot use the distance as 1.5 because the gravitational pull is acting downward. There is no component of the gravitational force that is actually acting in the x direction. We are assuming that this is the x direction here. The gravitational pull is acting down and the object is moving to the x. So basically, gravity is there, but there's no displacement with respect to gravitational pull. So in this case, we can say that distance is 0. In other words, gravity is not actually moving anything. So we are going to put 0 for that. So distance is 0, right? And that will give us 0, 0 what? 0 work, 0 joules. So here what we are saying is that gravitational force is doing no work. Okay. Now let's look at the work done by the support force. Work done by the support force. The support force is equal in magnitude to the gravitational force. So let's do work done by the support force. It will be the support force times the distance. The support force is the same as force of gravity, which is 2 kilograms times 10 meters per second squared. But there is no displacement along the y-axis, along the direction where the force is going. There is no displacement there. So the displacement is 0 in the direction where the support force is acting. For that reason, this force does 0 work as well. So remember, we are saying that displacement is 0 because the force is acting upward. We are talking about this force here. This force is acting upward, and there's no displacement along that direction of the force. And for that reason, our displacement will be 0 and our work is 0. Okay. Now, the other question you may ask is, what is the work done by the net force? You can also ask, what is the work done by the net force or the net work? Excuse me. The net work will be given by the net force. You multiply that by distance, displacement. Now, if you look carefully at our problem here, the support force cancels with the gravitational force, and the 5 Newton force and the 2 Newton force add up to 3 Newtons to the right. Remember, when the forces are acting in opposite directions, we find the difference, and the direction of the force is the direction of the larger force. In this case, the net force on this 2 kilogram object is 3 Newtons to the right. So I'll say that my net force is 3 Newtons to the right. Of course, it's plus, that's to the right. And displacement along that direction is 1.5 meters. So we see here that the network will be 4.5 joules, 4.5 J. All right. We can find actually the net work done by the net force also by just adding the work done by the 5 Newton force and adding that to work done by the frictional force. If you add 7.5 by minus 3, add that to that, you get 4.5 joules. All right, so the most important thing when you deal with work, we must ask work done by what? It has to be work done by a specific force. It has to be a force in question. Be careful of how you ask for work done. Very, very important. Now, let's look at this example. This example says that a 0.2 kilograms apple, let me write it there, kilograms apple, falls through a height, falls through a height of 3 meters. What is the work done by gravity? See, I have to emphasize what is the work done by gravity or gravitational force. Gravitational force. Some people just say gravity. All right. Here you are going to go and say, okay, work done is just force times distance, and make sure that the force and the displacement are parallel or anti-parallel. That is very, very important. The force and the displacement must be linear, must be acting linearly. Very, very important. So in this case, when gravity pulls the apple downward, displacement and the gravitational force are both pointing down. So this formula works and you can find your work. In this case, force is actually force due to gravity. That's one that is pulling the apple, or we call the weight. And the distance will be like the height. In this case, be h. When we multiply these two, we get our work. Force due to gravity is given by mg, and we multiply that by h. Then the work done by gravity, let me put fg here, work done by gravity. The work done by gravitational force will be mass is 0.2 kilograms times, I'm going to use 10 meters per second, times height. The height is 3 meters, 3 meters here. Now, when you do that, you should be able to get 6 joules. So this is 6 joules. That's the work done by gravitational force, 6 joules. All right, so let's look at another example. Okay, so work done by gravity here is 6 joules. Okay. All right, so what about this example? We have an 80 kilogram person, accelerates upward. Okay, upwards. Well, this is happening while in an elevator. Yeah, accelerates upwards at 3 meters per second squared through a distance or height or distance of, let's say, 4 meters. Okay, calculate work done by gravity. So question A, calculate work done by gravitational force. Question B, calculate work done by the support force, Fs. You know that when the person is standing in the on the elevator floor, there is a force pushing the person upward, and we call that one support force. We want to know how much work is done by the support force. And C, we need to calculate the net work done, on the person. All right, so this is the question. We need to analyze it. Now let's start answering it. First of all, we have to understand that, let's look at A. We have to understand that work done by gravitational force will be the force due to gravity times the distance. Okay, now I'll try to plug in the numbers. Since gravity is mg, I have to multiply that by distance, but I have to understand that gravitational force is acting downward and the displacement is upward. So I'll put a minus sign here to indicate gravity is acting downward and distance is upward. So plus here, and this is minus. That means the work done by gravity will be negative because gravitational pull is acting downward and the displacement is upward. Plugging, substituting, the mass is 80 kilograms, and times G, I'm going to use 10 meters per second squared instead of 9.8 meters per second squared. The distance is 4 meters, so 4 meters. That gives me work done by force of gravity will be equal to, that will give me what, let me see, that will give me 8 minus 800 here. Sorry, there's a minus here, minus 800 newtons for this part, minus 800 newtons, and times 4 meters here. This gives me minus 3,200 joules. That will be the work done by gravity. It is negative work because gravity is acting down while the person is moving upward. Now let's look at the work done by the support force. The support force is acting upward. Work done by support force will be equal to support force times the displacement. They are both acting upward. The displacement is up and the support force is up. So I'm expecting to get a positive work here. Now, to find the support force, I have to be very, very, very careful because this thing is accelerating. So I need to remember that a force diagram will help me. Remember, this is the mg and this is the support force. And we don't know how much that is. It's not equal to mg because this is accelerating. If it's accelerating, it means that the support force is larger than the gravitational pull. So it's larger. So I cannot conclude that Fs is equal to mg. That will be wrong. But I understand that I can apply Newton's second law of motion, which says that the net force in the y direction is equal to mass times acceleration in the y direction. The net force here can be given by the addition of the two forces. There is a support force which acts upward, and I add that to the gravitational pull which acts downward minus mg. That must be equal to mass of the object m here times acceleration in the y direction. This is Fs minus mg equal to mass times Ay, and therefore support force will be the gravitational force plus m times acceleration in the y direction, which you can also write as mg plus acceleration in the y direction. I just remove the bracket here. I just created a bracket. Okay, remove m outside, you end up with g plus ay. So support force will be, what was the mass? If you remember, the question says the mass of the person is 80 kilograms. 80 kilograms. So we are going to use 80 kilograms here times this is I'm going to use 10 meters per second today, and plus acceleration is upward, so it's gonna be how much? We are told that the acceleration is 3 meters per second squared, so I will put 3 meters per second squared here. That will give me my support force. Let me put it here. So the support force will be, let me see, together it's gonna be 1040. So 1040 newtons here. That is the support force. You see, the support force is more than the gravitational pull. Support force is more than the gravitational pull, because the gravitational pull, if you recall in this slide, we found the gravitational pull was 800 newtons. See, so here it is more gravitational, is more support force than gravitational pull. Now, anyway, let's find the work done. So the work done by this support force will be the support force times the displacement. And now we just found our support force as 1040 newtons. Then you multiply by distance. If you look at the problem, we are told that the distance, the height is 4 meters. The elevator rises to 4 meters. So I'm going to multiply by 4 meters. They are both positive, they're going up. Displacement is positive and the support force is positive. So this gives me the work done by the support force gives me 4,160 J. That's joules. Okay. So it is the work done by the support force is positive work. Now let's look at the work done by the net force. Now we have to look at the net force acting on the object. These are the forces. So the net force does how much work? Next slide. Work done or network. We call that network or work done by the net force will be the net force. Then multiply that by the displacement here. Now, if you look at our forces there, we had two forces. One was 800 newtons and another one to be longer. This one happened to be 1040 newtons. So basically the net force will be the 1140 is acting upward, so it has a positive sign, and then plus minus 800 because that's acting downward there in cross bracket. This should be equal to, oh sorry, this should be multiplied, this would be the net force actually, sorry, net force, and you are multiplying the, let me do this, you are multiplying the net force distance. Let's go back and remind ourselves what was the distance. Distance was trying to get a marker. Okay, the problem said that if you recall, it's 4 meters. 4 meters, that's the distance. So I'm going to multiply by 4 meters here. Now the net force, work done by the net force will be, our net force here will be, let's see, it's gonna be 960. If you try to do the operation here, 1040 minus 800, that will be let me see. 1040. No. So I just give you the whole answer. So it's 1040 minus 800. It's like what, 240 then times 4. So together will be 960. 960, yeah. Okay. Okay, you might want to do the operation. Just find the result here. Then times 4 meters. You should be able to get 960 joules. Now, if you look at the numbers we got before, if you look at the work done by, we started with work done by gravity and the work done by the support force. If we have the answers here, then it means that if I try to add up the two, I'll get work done by the net force here. So let's see. We initially found the work done by gravity was this one. So let's copy that. It was, oh, wait a minute. What was that? It was minus 3,200. Minus 3,200 joules. And work done by the support force, we found it here. It was 4,160. 4,160. 4,160 J. Now, if we try to add the two here, we should be able to get our network as 960, just like here. All right, so that should be the case. If we try to find the difference here, it should be 960. You can try that and see that is indeed got that. So basically, you could also find the network done on the object by just adding up the work done by gravity plus work done by the support force. You will find the same answer as this one. So same answer here. All right. Let's see, what about the work done when an object is acting at an angle? That will be interesting to look at the work done. I'm thinking about this situation where you have the box. Let me see, it has to be a straight line. Has to be a straight line. Oh God. It has to be a straight line. Okay. Okay, that looks like a straight line kind of. So I have my 2 kilogram object here, oh great. And now the force is acting at an angle. And this angle, I'm sure I want to make it 37 degrees. And the force is 5 newtons. Then the box moves through a distance. I later on see the box here. The box is here, 2 kilograms, but the distance here is 5 meters. The question is, what is the work done by the force? We are looking at work done by 5 Newton force. Okay, in this case, you cannot you cannot use this. You cannot just say work equal to force times distance, then you do 5 Newton times 5 meters. No, you cannot do that. This you cannot do. Don't do that, because the 5 Newton force is not acting in the displacement direction. No, it is at an angle. It's not linear with the displacement. For that reason, it is advisable to think about this force, because you can be broken down into 2 components. This component of force, and there is another component that will act upward like this, like this. Now, if I know the magnitude as 5 newtons and the angle, I can use trigonometry, or I can use scale diagrams like what we did some time back. we have to actually use a scale diagram and our knowledge of parallelogram rule. If we use parallelogram rule or trigonometry, we can find out what is the component of the force in the x direction, for example, and what is the component of the force in the y direction. So I have the answers for you. You can verify. So this component is actually 4 newtons, and this component here is 3 newtons. Okay, so I have broken down 5 newton into 2 components, into 4 newton in the x direction and 3 newton in the y direction. Now I can now look at the work done by the 5 newton force will be the work done by the 4 newton force plus the work done by the 3 newton force. So what I'm saying is that the work done by the 5 newton force will be equal to the work done by the 4 newton force plus the work done. My W is not good. Okay, work done by the 3 newton force. All right, so let's see what is the work done by the 4 newton force. That work now is in line or is linear with the displacement. I can multiply it, the positive 4 newtons, and then times displacement is 5 meters, plus the work done by the 3 newton force. Now you see we have the 3 newton force, of course, but displacement in that direction is 0. There's no displacement along the 3 newton force. So the displacement for that is 0 because the box is not moving towards that direction. It's moving actually perpendicular. For that reason, that will be 0. For this will give us the answer. 4 times 5 is 20 joules. So this is the work done because this goes to 0 here. So the work done by the 5 newton force is 20 joules. It's not equal to, if you were to multiply 5 newton times 5, you get 25 newton. But that's not the answer because this 5 newton force, not all of it is responsible for dragging the box in the x direction. It is just a component of the 5 newton force that is responsible for doing that. All right, so be careful. When the force acts at an angle, just get the component of that force in the x direction. The perpendicular component, like the 3 newton, doesn't do any work to the box. Okay, now let's look at this will be our next concept. That's power. We're going to learn something about power. What is power? Power is the rate of doing work. The rate of doing work. We find power by looking at the work done. Work done divided by time interval or time taken to do the work. That's like that. And we can have a simple example here or a brief example. Say that you lift a crate. You lift up a crate, a vertical distance. This you lift up a crate, a vertical distance of 2 meters in 1.6 seconds. Okay, you're using an 800 newton force. So you apply 800 newton force and you lift the crate a distance of 2 meters. Okay, so let's see. The question here is how much power is expended? How much power do you expend? How much power do you expend? How much power do you expend? This is the question here. Then you go and apply the formula. So power will be work over time. Now the work is the force times distance, remember? Force times distance over time. The force is acting upward is 800 newtons, and the displacement is 2 meters. Then you divide by the time, 1.6 seconds. This will give you your power. I hope if you do everything right, you get, I think, 1,000, because 2 times 6 is 2 times 8 is 1,600 divided by 1.6. I'm sure you should be able to get the answer as 1,000. 1,000. So 1,000 J's, and then down here you end up with the seconds. Remember, a Newton meter gives you a joule, and there's a second at the bottom there, so the units are joules per second. In physics, we usually say power, in this case, is 1,000 watts. 1,000 watts, abbreviated as 1,000 W. That's the power expended. Now you realize that if the lifting is done in a shorter amount of time, let's say 1 second, the power will be different. So if the lifting, let's say you do this fast, if the lifting is done in 1 second, then what do you see? Then the power will be, I'll just write here 800 newtons still. Displacement is the same, 2 meters, but then you do this just in 1 second. You're gonna see that the power here will be 1,600 joules per second. So actually more power. In other words, 1600 watts. And that's more power. So it has to do with time. If you do things, if you do work fast, then more power will be expended. If you are slow in doing the same amount of work, then less power is expended. All right, so let me stop here. I'm sure you have a better understanding of work and power. If anything, please let me know. I'll be happy to respond to your questions. Thank you for now, and thank you for listening. Bye for now.